Hi guys! In this video we're going to be looking at current in parallel circuits with branches of equal resistance, current in parallel circuits with branches of different resistance, and we're going to finish with a summary.
So we've previously seen the rules for current flow in series circuit, and we've also seen the rules for potential difference in series circuit and also potential difference in parallel circuits. So now we're going to look at what happens to current in parallel circuits, and first of all we're going to look at branches of equal resistance because it's simpler. Kirchhoff's first law governs the amount of current that flows into and out of a junction in a circuit. So this here is considered a junction. So it's where we have a split in our circuit and our circuit splits into two different branches. So the current going into our junction is equal to the current coming out of our junction. So we say current in is equal to current out. So we can see that the current out of our junction is split into two branches. So we're going to call it I1 and I2. So I1 is down one branch, I2 is the current down the other branch, which means we can write the current in as the sum of the currents coming out of this junction. So as the sum of the currents in the two branches. So we can say I1 plus I2, because that's the total current coming out of the junction. We just add the two together. In parallel circuits, there are a number of closed loops or a number of paths current can take. So in this parallel circuit, we can see we've got two branches. This junction here splits into two branches. So we've got one loop going along the first branch, and then we've got another loop going along the second branch. So we can see how we have two loops for current flow in this parallel circuit. So a parallel circuit has multiple pathways for the current to take, whereas a series circuit only has one path. These paths split and rejoin at what are known as junctions. So we've said we've got this path for the current, and then this path for the current. So we've got a junction here where we can see the paths split. So we can see that they split at that junction. And then at this next junction, we can see that they rejoin. So the paths split at one junction and then rejoin at another. Kirchhoff's law tells us that at each junction, the total amount of current into the junction equals the total amount leaving the junction. So if we look at this first junction here, we've got a certain amount of current going in, I in, and then the current splits. So we've got I1 and I2. But Kirchhoff's first law tells us that the current going in equals the current going out, which means the current going in is going to equal the sum of these two currents. So the current going in is equal to I1 plus I2. Then if we look at this next junction, the current going in is I1 along with I2, and then the current coming out of this junction is the current out. So we can see here that the current going in is I1 plus I2, and this must be equal to the current going out of the junction. So that's what we get from Kirchhoff's first law. Current in here splits into two, and the current going in is equal to the sum of these two currents. Then this junction, we've got two branches of current coming in, and then the sum of these two currents gives us the current going out of the junction. We can see that the current that leaves the cell is equal to the current returning to the cell. So the current that's leaving the cell, which we're going to call I leaving, splits into these two branches, I1 and I2. And we said according to Kirchhoff's first law, that means that I leaving must be equal to I1 plus I2, because the current going into this junction, which is I leaving, must equal the current going out, which is the sum of these two currents. Then if we look at this junction here, we've got I1 and I2 entering the junction, and then leaving the junction, we have I returning. So that's the current returning to the cell. So we can again see from Kirchhoff's first law that I returning is going to be equal to I1 plus I2. Current going in, which is I1 plus I2, is equal to the current going out, I returning. So we can therefore see that the current leaving the cell is equal to the current returning to the cell. So these two are equal. They're both equal to I1 plus I2. So this ensures that Kirchhoff's first law holds through the cell. So we've said that the current coming out of the cell, I out, is equal to the current going into the cell, I in. The current leaving is equal to the current then returns. At a junction, the amount of current that flows through each path leaving the junction depends on the resistance of the path. So we've got I1 here and I2 here, where our current has split at the junction. So the amount of current that actually goes through that particular branch depends on the resistance of that path. So we've got R1 and R2. So a higher resistance is going to resist the flow of the current. So that means less current will go through the branch with a higher resistance. If we've got a lower resistance, that means there's less resistance, so more current is able to flow through. But if we have two identical resistors connected in parallel, then the resistance through each branch will be the same. So now let's imagine that R1 and R2 are actually equal. So that means we've got two identical resistors in both of our branches. So we've got the same resistance in each branch. So in this case, the current is split equally at the junction. So if we've got a resistance R here and an equal resistance R here, when the current goes into the junction here, it's going to be split equally into I1 and I2. So I1 will equal I2. And that's because we've got the same resistances, so both resistors will provide the same resistance to the current that wants to flow through the branch, and if the same resistance is provided, then the same current is going to be able to flow through. So let's apply what we've learned about current in parallel circuits to an example. A cell is connected in parallel to two identical resistors. If the current flow out of the cell is 5 amps, what is the current through each of the resistors? So we've been told that the current flow out of the cell is equal to 5 amps. So the current measured at this point here is 5 amps. So we've got our current going in. And this then splits at this junction. So we've got I1 here and I2 here. And we want to know what these are. But we've also been told that these two resistors are identical. And the other thing to note is that the current that then comes out of this second junction is also equal to 5 amps because our I1 and our I2 then recombine here. So our first step in solving this problem is to write Kirchhoff's first law. So that tells us that the sum of the current going into a junction is going to be equal to the sum of the current coming out of that junction. Our second step is to write the summation in terms of the different paths for current given that the current in both branches is identical. So the current going in that junction is going to be equal to I1 plus I2, so the current that it splits up into. But we've got two identical resistors, which means that the current split is going to be equal. So we've got the same amount of current in both branches. So we can therefore rewrite this as 2I1, because it's as though saying I1 plus I1, which is 2I1. And this would be the same thing as writing 2I2. It just depends on what notation you decide to follow. But the key thing here is that the current that goes through each of these two branches is the same. So the current is split equally at the junction. Our third step is to rearrange to make the current in each resistor the subject of the equation. So we're going to divide the current in by 2. So we get that I1, the current in one of the two branches, is equal to the current going into the junction divided by 2. And now our fourth step is to substitute values into the equation to solve for the current through each resistor. So I1 is going to be equal to the current going in, which we said was 5 amps, because that's the current that's leaving the cell, divided by 2. So this means that the current that goes through each resistor is equal to 2.5 amps. So now let's consider the current in parallel circuits where we've got branches of different resistance, because this is actually a bit more complicated. So sometimes the resistance across each branch of a circuit varies. So for example, we've got two resistors here in our circuit on each branch. We've got R1 and R2. And in this case, R1 is not equal to R2, so they're not equal resistance. We know that the sum of the potential differences across each branch must be the same due to Kirchhoff's second law. So Kirchhoff's second law tells us that the sum of the EMF in a loop is equal to the sum of the potential differences of the components in that loop. So for example here, this cell here provides an EMF E. And we've got a potential difference V1 across this resistor and then a potential difference V2 and V3 across these resistors. And Kirchhoff's second law tells us that the EMF provided is equal to V1 because we're considering this first loop here. And we've said the EMF provided in that loop is equal to the potential differences across the components in that loop. So the EMF is also going to be equal to V2 plus V3. And that's because if we consider this loop here, the EMF provided to that loop is still E. But now in this loop, we've got two resistors. So we need to add the potential differences across both of them together, which is why we've got V2 plus V3. Since the potential difference across each branch is constant, the current through each branch must be inversely proportional to the total resistance of the branch. So we've said that the total potential difference across each branch is the same because that's equal to the EMF. So we can therefore say that R, the resistance of that branch, is equal to the potential difference across that branch V divided by I. So we're saying that R here is the resistance of the whole branch, and the current I is the current through that branch, and then the potential difference V here is the potential difference across the whole branch, which is equal to the EMF. So that's why we're saying that this potential difference across the whole branch is constant. It's equal to the EMF of the cell, and the EMF of the cell doesn't change as current flows through the circuit. So we can therefore say that if the potential difference across the branch is constant, the resistance across the branch is inversely proportional to the current. So R is proportional to 1 over I. Paths with greater resistances will allow less current to flow through and vice versa. So we've got a resistance R1 here and a resistance R2 here. So let's say R1 is greater than R2. When our current splits at this junction into I1 here and I2 here, so less current is going to flow through the resistor with a higher resistance. And this is because we've seen previously that a higher resistance means a bigger resistance to current flow. So it allows less current to flow through it. So if, in this case, R1 is greater than R2, that means I1 will be less than I2. So the second resistor with a lower resistance R2 is going to resist the flow of current less effectively. So that means more current will flow through that branch. So let's apply these ideas to an example. Two resistors are connected in parallel to a cell. One of the resistors has double the resistance of the other. If the current through the cell is 9 amps, find the current through each branch. So we've been told that we've got two resistors here, and one resistor has double the resistance of the other. So if we say the resistance for this resistor is R, the resistance of this other resistor is 2R. And we've been told that the current going through the cell, so the current that actually enters this junction here, is equal to 5 amps. And it then splits into two branches, I1 and I2. And we want to know the value of the current I1 and the value of the current I2. And this is going to be affected by the different resistances through each branch. So our first step is to write the equation for Kirchhoff's first law. So the sum of the current going into a junction, we've seen, is equal to the sum of the current going out of that junction. Our second step is to apply the equation for Kirchhoff's first law to this circuit. So the current going into that junction Iin is going to be equal to the sum of the two currents that it splits into, so I1 plus I2. Our third step is to write an equation for the resistance in terms of potential difference and current. So we know that the resistance of a component is equal to the potential difference across that component divided by the current. Our fourth step is to rearrange the equation to make current the subject. So we're going to rearrange this equation, we're going to multiply both sides by current and divide both sides by resistance. So we end up with I is equal to V divided by R. Our fifth step is to write the equation for the current through the first branch. So I1 is going to be equal to V1, the potential difference across that first branch, divided by R1, the resistance of that resistor, which we've labelled as R. So we're going to say V1 divided by R. So that's our current through the first branch. Our next step is to write the equation for the current through the second branch. We've called this I2, and this is equal to V2 divided by R2, so the resistance of that second resistor. However, remember we said the resistance of the second resistor is double the resistance of the first resistor, which means we can rewrite this as V2 divided by 2R. Our next step is to write the relation between the potential difference across the first and second branch. So we know that across both of these branches, the potential difference doesn't actually change, it's the same, because the potential difference across each branch is equal to the EMF provided. So we say then that V1 is equal to V2. Our eighth step is to calculate the ratio between the current through the first and second branch. So we're going to do I2 divided by I1. So we said I2 was equal to V2 divided by 2R, and then we're dividing this by I1, which we said was V1 divided by R. So when we multiply two fractions together, we make sure to multiply the first fraction by the reciprocal of the second. So what we're doing here is we're doing V2 over 2R multiplied by R divided by V1. But remember, we said that V1 and V2 are equal, so these two are going to cancel. And we can also see that R and R are going to cancel as well. So this leaves us with I2 divided by I1 equal to a half. So we can therefore say that I2 is equal to a half I1. Our ninth step is to substitute this ratio into the equation for Kirchhoff's first law to find the current through the first branch in terms of the initial current. So the current going in, we said, was equal to I1 plus I2. And we've now found that I2 is equal to I1 over 2. So we've got I1 plus a half I1. So this gives us the current going in as equal to 3I1 divided by 2. Now our 10th step is to substitute the value for the initial current into the equation for Kirchhoff's first law to find the current through the first branch. We've been told that the current going through the first branch at the beginning is equal to 9 amps. So that means 9 amps is going to be equal to 3 divided by 2 times I1. So we can rearrange this for I1 to get that I1 is equal to 2/3 times 9 amps. So that means I1 is equal to 6 amps. And finally, we just need to substitute the values for the initial current and the current through the first branch into the equation for Kirchhoff's first law to find the current through the second branch. So the current going in is equal to I1 plus I2. So 9 amps is going to be equal to 6 amps. We said I1 was 6 amps plus I2. So I2 is going to be given by 9 minus 6, which means I2 is equal to 3 amps. And we can see that I2 is indeed equal to I1 divided by 2. Because we said I1 was equal to 6, and we can see that I2 is half of 6, which is 3 amps. We see that if the resistance through one branch is double that of the other, the current through it will be half as large. So we've got I1 here, and we said we've got a resistance of R here and a resistance of 2R here. So we saw that the current going through the branch with half the resistance is twice as big as the current going through the branch with double the resistance. So we've got I1 divided by 2 goes through the resistor with resistance 2R, and then I1 goes through the resistor with resistance R. So we can see that the current is inversely proportional to the resistance.
Hey guys! I hope you enjoyed the video. If you're looking for an amazing A-level physics resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together let's make A-level physics a walk in the park.